Now we'll be doing a question on line-to-line fault. So it's for a line-to-line fault. So you know where to look for the formulas for calculation of these parameters. So what we have to do is we have to again draw an equivalent symmetrical component network, and then we have to calculate the fault current. Now let's see how does the situation looks like in this case. So we have a generator. Now let's say we mark the three phases three lines A, B, and C. So this is a line-to-line fault. So let's say the fault is here between lines B and C. So the fault current is right here, right? And if we mark rest of the current, so IB is here and IC is here, all right? Now if we try to summarize a few things which we can summarize from this diagram, one thing is that the current IB equals to negative of current IC because they are flowing in opposite directions. The other thing is the fault current is same as that of current IB, or even you can say that negative of IC either one of them is true. The other thing is since both of them are connected together, so the voltage at those 2 points is same now. Now, since our target is to draw the symmetrical component network, so we need to know which parts of the network will be present out of positive, negative, and zero sequence, and which configuration they will be put together. And again, the positive, negative, and zero sequence networks for a generator still stays the same. So let's have a look where we relate the sequence currents to phase currents. So these are the three sequence currents which we need because we need to have a diagram drawn. And there is a 1/3 here. And so here it's IA, which is 0 in this case, IB is IB, and IC is negative of IB. So if you go back to the diagram, so let's do that. So IA is 0, IB is IB as it is, IC you can say that negative of IB. Right? So this is your IA, which is 0, this is IB itself, and this is IC, which we have replaced with negative of IB. Now if you try to simplify it, IA 0 comes 0 plus IB minus IB, which gives you 0. That means in the complete sequence network, there will not be any zero sequence network present. The second thing is if you look at IA plus equals to 1/3, of course, there. So 1 times 0 is 0, A times IB minus A square times IB. So we can say that A minus A square and then an IB. And IA negative equals to again 1/3, 1 times 0, A square times IB, and A times negative of IB. So this is what we get. And if we compare these two, so they are just negative of each other. So it could be written this way. 1/3 A minus A square IB. So that means what we can conclude here is IA positive is same as that of IA negative, or IA negative is same as that of IA positive. So what that concludes, in the complete network, there is no negative sequence network present, and the positive and there is no zero sequence network present, and the positive and negative sequence networks will be connected in parallel. So this is your positive sequence network for a generator. Positive sequence reactance in this case is 0.3. J 0.3, and the voltage source is 2 angle 0 in per unit, so we don't need to change anything. And the negative sequence network is having a value of J 0.4. Now to connect, so let's say this is positive, this is negative, this is positive, this is negative. So to connect them in parallel, the positives has to be connected together, the negatives has to be connected together. All right, to mark the currents in here, so here is IA positive and here is IA negative. So if you see, they are flowing in opposite directions, so this is true. And there is no zero sequence network, so IA 0 is 0. Now, the fault current, because our aim, so this is your part A. So this is your part A, this whole thing. It's a symmetrical component network. Equivalent symmetrical component network. Right, so we were saying we have to calculate fault current. So if you look into your formulas, the fault current is given by minus J square root of 3 IA positive. Right? So we have to find IA positive, which we can easily find from this network, and then we have to multiply it with this part to get IF. So let's find IA positive. IA positive in this case is given by 2 angle 0 divided by J 0.3 plus J 0.4. Right? Now this formula you can find in your formula sheet as well. So where it says it's generator voltage divided by Z positive plus Z negative, how you write this in its generic form. So IA positive equals to 2 angle 0 divided by J 0.7, and again J is 90 degrees, so 0.7 angle 90 degrees, and if you do the calculation it brings you 2.86 angle again negative 90 degrees in per unit. So that's your IA positive. And then your fault current, this is your part B, part B, equals to minus J square root of 3 times 2.86 angle minus 90 degrees. So here J is again 90, so you can convert it to 90, minus is minus there, 90 degrees, square root of 3, sorry, I just put an angle, let me erase it. So square root of 3 times 2.86 angle 90 degrees. So this 90 and 90 will bring you an angle of 0. So you're left with square root of 3 times 2.86, which comes to negative 4.95 in per unit. So that is your fault current.